Okay, let's get going here. We're going to pick up where we left off last time, talking about, we're going to finish up some discussions of Ampere's law. And so we had left off at this point here. So we're looking at a solenoid, a big, basically, cylinder wrapped up with wires, current-carrying wires. And we had gone through and talked a little bit about the solenoid, and we hopefully had see the fact that basically when you got a solenoid, it's going to have a really big magnetic field going this way here. And you can use the right-hand rule, right? You put your fingers in the bottom of the current, come out the top, and your thumb points that way. And we argued by just looking at sort of the setup of the wires that the magnetic field outside of the loop is going to be really close to zero. And the part where we left off last time, we're going through and doing Ampere's law. So we got the B dot ds, and we did that part. And we looked at the four contributions. And so there's 1, 2, 3, 4. And again, we're trying to find, this line integral of the magnetic field over these segments. And so when we added this up, we like to do it sort of segment 1, segment 2, segment 3, segment 4. Segment 1 was just that case where the B field is parallel to your segment the whole time. And so the answer is just the magnetic field times the length of your segment. Side 3 is easy. The magnetic field in that region, well, I shouldn't say easy, but is, can we just sort of say, well, the B field out here is 0. And so, you can just think about it here as being even 0 times L, if you want, would be the guy there. And then because this magnetic field here is perpendicular to 2 and 4, and then over here it's just 0, there's no contribution from those two either. And so you get basically a bunch of zeros added up with B times L for that piece prior. So I just wanted to stop. We asked about questions on that last time, but we finished up there. So anybody questions on that? So with this Ampere's law, it's like Gauss's law. If we want to find out the magnetic field of something, we can sort of look at the left-hand side, the right-hand side, make them equal, and we can go through and develop a magnetic field for the region that we're interested in. And so now let's look at this one here. So now I'm going to look at the current enclosed in the loop, right? And so here, the current I is the current going through all these different wires that coming, out on top and on the bottom. So what would be the current enclosed, the total current enclosed for the Amperian loop below? And the way I phrased it, just sort of imagine that in all the pieces there's a mu naught there. So I dropped the mu naught from the answer, but assume there's a mu naught in front of all of them there. Okay, so let's look at this. I think we've had time to think about it. And so again, just to be complete, unitly good, we would want to put a mu naught into all of these things here. And so if we look here, so let's just think about this. If you look at our solenoid, right, so our solenoid is this big, basically, thing with wires wrapped around it. Each one of these wires has a current I in it. And so there's a current I there, a current I there, one there, one there, one there. If you count them up, there's 12 current I's, okay, included in my loop. Okay, now that loop was kind of arbitrary, but that's just how I chose to draw it. Okay, so there's 12 currents. And again, the way we think about this is you imagine like you took that loop and dipped it in soap and came out and there's like a soap film on that loop. Okay, you want to look at how much current is piercing through that soap film. And so here it would be 12 times whatever the current is. Okay, questions on that? That's a tricky one. And so then what we can do, again, similar to what we did with the Gauss's law stuff from a couple weeks prior. Yeah, not even sure how to do that again. And so we would set up this B dot ds equals mu naught times I. And I'll go over here and just stop this one. So I think at this point we probably, yeah, so the correct answer is in there, but there was a lot of people that said just I. So we want to make sure definitely hit home. But if I'm writing this out here, okay, we did our B dot ds, and so I got B times the length L. Again, that's the length L in this picture. And over here it equaled mu naught. And what I'm going to say here is I'm going to call it N times I. So it's sort of how many turns I have. You know, for us it turned out to be 12, but I'm just going to call it N because I could make the size of that thing differ depending on what I was wanting to do with it. And so then when we solve for our magnetic field as a function of R, we find this is the equation we got last week. All right, so it's mu naught N divided by L, so it's the number of turns divided by the length, okay, which is what that is there, times the current. And so it does not actually depend on the distance R. So it's similar, again, like the analog would be the capacitor. This is how you would, the easiest way for us to create, or one of the easiest ways for us to create a constant magnetic field. And we're using this idea of Ampere's law, which we'll get some more practice with next week. But questions on that there? Anybody? So on the one hand side, you're trying to find out your magnetic field, the line integral. And again, it boils down to one of those two kind of cases. So the key part is to kind of figure out what your magnetic field looks like. And on the other side, it's how much total current is piercing through that soap film. Questions? Okay. And this is the same slide we showed before. So again, this is sort of the end result. We can show this using Ampere's law. It's the easiest way to show this, the magnetic field from a solenoid. All right, so far we've done a couple of things. So we've talked about how moving charges create magnetic fields. We looked at the atomic level a little bit, also currents in a wire. And we looked at how B fields exert forces on moving charges. So current-carrying wire feels a force. So we've talked about these things here. So charges and magnetic fields seem to be intertwined. And so now we're going to complete everything and sort of show a pretty important thing that a change in a magnetic field causes moving charges. So sort of completing this circle. So showing you that. So we've sort of showed that changing electric charges creates magnetic fields. We're going to do the same thing here. And so here's some questions from students. So do magnetic fields come hand in hand with moving charges? Yep, because a moving charge causes a magnetic field, and a magnetic field causes moving charges. And so if you have one, does that mean you spontaneously will have the other? And yeah, I think we're going to agree with that. With this idea that it has to be a changing magnetic field. This sort of be the key part there. And so this is going to be what's called Faraday's law. And so we're going to talk about this in the next couple of lectures. And this is a pretty key thing in this idea of E and M. I don't know if you've ever heard that, but E and M is something, electricity and magnetism. So we're going to find that electricity and magnetism are intertwined. In fact, they're really just two different sides of the same thing. And so this is Faraday's law is a key to things like generating electricity, microphones, speakers, amplifiers, electric guitars, so lots of stuff. So basically I would say a lot of different things we do with electricity depend on this law. So it's really important. So we're going to spend some time talking about this. And to start off, we're going to, again, just show a couple of things. So this idea was first seen in this experiment here, okay? And so Faraday discovered this, and basically what he did is he just had a loop of wire, and he discovered that if you put a magnet inside that loop of wire, all right, and move it, okay, over here, all right, this thing is an ammeter, so it measures the current that's going through this wire. You can create a current going through that wire. And we just have a real simple setup here. So this is an ammeter. It measures the current going through it. And here we just have literally just solenoids, okay, little tubes of wires wrapped around them. And so if I take this thing, which is a pretty strong magnet, and kind of push it in and out of here, you'll see that this thing will deflect. If I can get it in there. Okay, and so it sort of depends on the size of the loop here, sort of the more loops. And so what I'm actually doing here is just by putting the magnet into this wire, I'm creating a current going through these wires. And it can get pretty big depending on which one of these. And this has to do with just sort of the number of loops and the resistances in the wires here. But this is the effect of Faraday's law, that a changing magnetic field creates an electric field. Now, electric field makes the current go through the loop. And so this is, again, pretty key thing. And so we're going to go through and sort of try to understand this as best we can. And so we're going to call this current that I just created, that we can create the induced current. And so we're going to start with an example of a situation where we can, hopefully, looking at stuff that we've learned, understand what's actually happening to the charges. Okay, so we can actually start with a picture where we can see pretty clearly what's happening and kind of explain it to ourselves, and then we'll try to move this into a more generic statement which can handle cases where it's not as easy to look at it as sort of microscopically as we are here. But here we have just a piece of metal, some bar of metal, really boring, and I'm moving it through a magnetic field. And if we take our right-hand rule, okay, so you take this bar, which is a piece of metal, it's a conductor, so it's got charges that are free to move, and if you move it this way, okay, so we take our flat right-hand rule, right, and say, okay, my thumb goes with the velocity, my finger is going with the magnetic field, the force on a positive charge would be upwards, like here. Okay, so the magnetic force on a positive charge would be upwards. And that's just stuff that we talked about, last week. And by the same token, you can do it with the right-hand rule and say that negative charges will be pushed down. Now we know in reality, it's the negative charges that are really the ones that are moving. But it's good to kind of have a feel for both, just because it helps you kind of understand what's happening a little bit better. And so in this case here, just by moving this bar, we're going to create a separation of charges. Okay? So by moving this thing here through this magnetic field, I create a separation of charges. So what will happen is there'll be a bunch of negatives here and a bunch of positives here, creating an electric field. Okay? And again, hopefully you can see exactly where this is coming from, just kind of from our description. And so why does a change in a B field causes moving charges? So that was a common question last night. And so, like I said, in some cases, like here, you can kind of show exactly where it comes from. In a lot of cases, it can be tricky to kind of break it down and actually see. You can always do it with your right-hand rules, but it can be really tricky. But so we're trying to kind of show you the nice system where you can see exactly where it comes from, and then kind of moving on to more diverse cases. And so this thing they call the Motional EMF. And so EMF is electromotive force. We sort of talked about it like kind of being the battery. And so if I slide this bar through this magnetic field, what's happening is I'm creating, in a sense, a little battery. There's a positive and a negative side. And if I was to go into here and connect the two sides with a piece of metal, okay, current would flow through it. Okay, so if I was to sort of just connect a wire from the two ends here, we would complete a circuit. And so this is the idea of motional EMF. So by moving this bar in a magnetic field, I've created an EMF, which again, we treat similar to a battery. Okay? And so here's the picture, and we'll show you in a second or a little bit how this works, but we're just going to tell you that so the size of this battery, the voltage of it, will work out to be this over here. It'll work out to be the velocity, sort of how fast you're pushing it, the length of the bar, and the magnetic field that you're pushing it through. Okay, so hopefully you can kind of justify where those three things come from, and once we get to a more quantitative picture, we'll show you exactly how you can derive that as we move on. And so let's try ourselves a question here. And so this is the same sort of idea, just to see if we're all kind of following along, but we've changed the orientation, right, like we'll often do. So here we have a metal bar moving through a magnetic field. The magnetic field's pointing out at you guys. The metal bar is moving down. I want to know is what sort of distribution of charges are we going to accumulate on this metal bar here? So discuss with your neighbors and see what you think. Okay, so I think most of us have voted here, and I do agree with the majority. So B is the majority here, and I agree with that. So again, if we take this, so this is the flat right hand rule. I mean, the good news is by doing this, we're getting practice for our magnetism stuff, right? So we take our flat right hand, we take our thumb in the direction of the velocity, which would be down, and then my fingers point in the direction of the magnetic field, which would be out towards you guys. And so my palm would be the force on a positive charge. So the positive would move that way, and the negative would move that way. Now, again, in reality, it's just the electrons that are moving, but the electrons are going to move in a way such to leave those positives back there. Okay, so it works exactly how we'd want it. And so you'd get some positives over here and some negatives over here. And that's, so if I do my right hand rule, the force from magnetism on the positive charges would push that way there, okay? Again, using that rule. So questions there? And then what we can do with that is then look at questions of this sort here. And so this is the kind of thing that we'll have pictures of, something like this. So here's this weird kind of setup they devised, but it's just we're trying to learn this stuff here. And you can totally do this, but you set up a metal bar that's like, connected to some wire or something like that, so it sort of slides back and forth. And if I slide it this way, where we get positives there and negatives there, and what will happen is since this thing here is a wire, a conductor, a current will go through it. And so the current, we use V equals IR. Here, remember that your voltage is this EMF business. Right, so the EMF, and so in this case, this is sort of a case where you can kind of see why they call it EMF, because it's not really a voltage of a battery, it's something that can be changing, okay? So it changes depending on how fast you go or what the length is or whatever, these things can change here. And so, but it's your voltage, which is your EMF divided by the R. And so that gives you your current flow, and so you can have a current flowing through here. And so here's an example of this idea of Faraday's law. So in this setup here, just by moving this bar, you create this induced current. And induced currents, you're going to find, are everywhere. So I don't fully understand the difference between EMF and voltage. Again, in a lot of cases, it's sort of, we treat it similarly here. But here's an example where, so this is not a real battery doing this. And so they give it this separate name of electromotive force. But in reality, you can, again, think about this as a little tiny battery. All right. And now here's the other thing about this, which is important, is that when you push this bar, okay, there's going to be a force on you in the other direction that's trying to stop it. Okay, so we're going to see that in general, nature doesn't like when you create induced currents, because what are you doing? You're creating energy. All right, so nature is going to apply a force to kind of go against you. And so again, in this case, so if I'm pulling this way, Okay, in that picture before, we showed that the current is going this way here. And so now, if you do your force law on that current, okay, so you sort of take your thumb going upwards with that current, your fingers point in, then the magnetic force will be this direction here. So the force, there'll be a force on this current going through your bar that opposes the pull you're doing, okay? And so nature is going to want to try to stop you. We'll see that this is a general trend too. Okay, and then the other thing too is it would be really bad if when you were pulling this, if nature sort of pulled the same way, because then nature would sort of be helping you create this energy, right? Because an induced current, you can light a light bulb with it, it's energy, right? And so basically you've got to overcome this force in order to push this and make this induced current happen, okay? And so a device that does this, that converts mechanical energy, so in this case me pulling it, all right, into electric energy is called a generator. And this is the basis of all generators. You have better setups than this, but this is the fundamental idea of how a generator works. And so here's an example of a kind of problem that you could sort of solve now. So I'll just go ahead and do it because it's not that tricky of a problem. But, so you'll have this sort of setup like this. They tell you the length of the bar. They tell you the velocity of the bar, the magnetic field. They want you to find the current. And so it's literally just that equation we had a little bit ago here. So the EMF, actually that's the velocity, pardon me. And so a velocity of 4 meters per second, a length of 1.5 meters, and a magnetic field of 2 Tesla divided by 2 ohms. And when I did this, I got the answer of 6 amps. So you can go through and get the current to come out in a case like this. Okay, so let's look at the one we had from last night. So I think people did pretty good on this one, so I won't spend too much time on it, but let's take some seconds here. Try to convince your neighbor of what you thought from last night, and then we'll see what we get. But it's the sort of same setup we were just talking about, and we want to know is exactly which way will the current be flowing here. Okay, so I think I agree with the majority. I think we improved on our responses from last night, so it looks like you're convincing your friends, which is good. So I get counterclockwise. So this is the same. We're going to find different ways to do this, but for right now, the way we would probably think about this is you'd put your thumb with the velocity, my fingers point out to you guys, and my palm points that way. So in this case here, when I do that, that's going to give me positive charges on this one end. Okay, so the positive charges will be over here, and the negative charges will be over here. Okay, and so when we do that, or I'm sorry, I'm backwards. Beg your pardon. Which means that the current, our conventional current, which is the current we're always going to be talking about in a case like this, will flow from positive to negative in the counterclockwise direction. So that's how we would look at a problem like that right now. We'll find alternate ways to look at that later. Questions, anybody? So right now, the easiest way, and so again, this is one that we can actually look at microscopically, which is helpful with this kind of stuff. And so actually, I think this slide we'll wait till next time to talk about. Okay, so we've seen some examples of the phenomenon. We just looked at a case where you can actually, microscopically see what's happening. And so now we want to delve more into this and try to understand a little bit more about it. And so we're going to talk about this concept of magnetic flux. And so magnetic flux is similar to electric flux, just that it's dealing with the magnetic field. Okay? And so if you remember, the electric flux was like E times A times cosine of the angle. It's going to be the same thing here, just dealing with the magnetic field. Okay? And so the flux, again, has this symbol. And so BA times cosine. Again, this cosine angle is the angle between your magnetic field and a vector that's perpendicular to the surface that you're talking about. Okay? And so again, you can think about this qualitatively as the number of magnetic field lines that are piercing through your surface is what the magnetic flux is measuring. Okay? And so what does the magnetic flux tell us about a circular looped wire? If the wire does not have an enclosed area, what happens to its magnetic flux and why? And so it's the same sort of idea. Like this idea of the flux is really general, and it works for any kind of areas you want. Okay, so it doesn't have to be a square area or whatever. It can be any kind of area you want. It's pretty flexible. And so here's just another kind of version of this. For the units of this, area times magnetic field would be units of Tesla times meters squared, which we have our own term for, the Weber. And so magnetic flux would be measured in Webers. And again, it's really similar to electric flux. If you've seen that, we've seen that before with Gauss's law, so we should have some familiarity there. And also just this idea, the angle that you measure this from is the angle from what we call the area vector, which is this vector that points perpendicular to your surface. So here's some kind of a loop that's doing this in this particular case here. And so that would be what you do for that one. Okay, and so now what we're going to sort of talk about is this idea that the magnetic flux can change. And so let's look at some cases here. Okay, so the magnetic flux is the sort of number of magnetic field lines that are going through some surface. So in this case here, is the magnetic flux through this square changing as I move it along with that velocity there? What do you guys think? Is the magnetic flux there through that changing? Okay. And so I think I agree again with the majority here. So I'm going to say no for this one. So we get no. I think that's where most of us are at this point. And so what's the idea? Well, basically, if you look here, you could kind of argue, again, the way to think about the magnetic flux is how many field lines are coming out. So as you move this way, right, you're going to make these 4 lines disappear. But since this is a nice uniform field, these 4 lines here will come into play. Okay, so as you lose some, you gain some. So since it's a nice constant field, you're not going to have any loss in this thing we call the magnetic flux. And so in order to have the change in the magnetic flux, you got to do something like this. And so in this case, we're rotating this loop. Okay, so like right now, you got like a total of 16 magnetic field lines going through it. And so as this thing rotates, right, you can kind of imagine, so it starts out like this, and it'll rotate to where it's, sort of, its edge is straight on with you guys viewing it. And at that point, none of the magnetic field lines are going through it. So as you rotate this thing in this magnetic field, the magnetic flux through your loop is going to be constantly changing. And so this is going to be the kind of the case where we're going to have this effect. Okay, when the magnetic flux through your loop is changing, you're going to have an induced current. Okay, where in that last case, you are not going to have an induced current because the magnetic flux is staying the same. So our job is going to be to determine when that's happening, and then when it is happening, if we can try to figure out which way the current is going. Okay, so we're going to kind of answer the same questions we just answered for that other situation, but just for more general situations. That's what we're going to try to do. So this would be a yes for the magnetic flux through it changing. And so here's how you look at one of these problems. And so here's, I'm not sure if this is one from last night, but this is a similar one. And so now we have this loop, and we show the magnetic field going through it. And so a magnetic field goes through a loop of wire as below. If the magnitude of the magnetic field is increasing, what can we say about the current in the loop? And so what we can say is this here. So I'll show you sort of like how I think about these things, and then we can kind of go through and talk about it. And so when we're talking about this thing called Lenz's law, which the video talked about, and so what I like to do is I'd sort of like to draw two pictures, a before and an after. Okay, and so in this case here, so a magnetic field goes through a loop of wire as below. If the magnitude of the magnetic field is increasing, what can we say about the current in the loop? Okay, and so what they're asking about is the induced current in this loop. And so if the magnetic field going into the page is increasing, all right, you're going to, if you look at your picture, so like say, for instance, like right now we have, say, 4 magnetic field lines going in. If it's increasing, then that means at some later point there's more. So maybe now there's 5 magnetic field lines going in. And this kind of goes along with what we were saying before. Okay, so this Lenz's law, the way it works is nature wants to create a current, all right, that's going to make a magnetic field that tries to get the flux through your thing back to where it was before. Okay, and this is really kind of tricky when you're first seeing this. And so what nature wants to do is it wants to take the after and make it look like the before. Okay, so it wants to make a magnetic field pointing out to you guys to sort of cancel that extra field line that was going in. And so that would be a magnetic field that's going in the counterclockwise direction. So the induced current would go that way there. Okay, and so in this case, it would be a counterclockwise current. I can't remember if this is the one you guys did last night or if you did a similar one, but that's sort of the thinking there. So questions on that idea? And it's really tough because I think a lot of people want to sort of automatically sort of make your current sort of go along with the magnetic field that's there, but it's the change in the magnetic field, and that's the really tough part. So you want to make your after picture look like the before, and so to do that, you would want a magnetic field pointing out at you guys to sort of cancel that last one, and that would be an induced current going that way there, okay? And so you can look at these pictures to try to understand the different examples that we're doing. So let's try one ourselves here and see how we do. So a magnetic field goes through a loop of wire as below. If the magnitude of the magnetic field is decreasing, what can we say about the current in the loop? So go ahead and think about this one and see what you think. Okay, so let's look at this. Again, I think I agree with the majority. Now, one of the tough things about this topic is there's only 2 answers, and so if you ask one that's similar to the last one but opposite, you can kind of say, well, I'm going to guess it's the other one. But let's go through and make sure that it makes sense. So I agree with the majority. So before, we'll do the same picture. There's like 4 field lines going in. Now, if you decrease that field, at some time after, there'll be sort of one less line pointing in. And so now the magnetic field that nature wants to create, nature wants to keep, so nature doesn't like changes. It wants to keep the magnetic field going through this loop the same. And so you'll have a magnetic field that there's a magnetic field going into the page to sort of add that extra line in there that it just lost, and that would be a clockwise current. Okay? Would be the case for that one there. So again, I think most of us got that. So that's good, but you definitely want to do some more practice on this. So questions on this, anybody? Like I said, this can be a tricky thing when you're first getting into it. So let's try a harder one now. So the bar magnet in this picture is pushed towards the center of a wire loop. Which is true? So in that wire loop there, is there going to be a clockwise, counterclockwise, or will there be no induced current? What do you think? Okay, so let's talk about this one. So it's got a lot going on in this one here. So first of all, I'm going to draw the same kind of pictures I drew before. You know, the before and after. So this is one, like a lot of them will be, where you've got to sort of think about a couple different things. So the first thing, we got to think about, how does our magnetic field lines coming off of something like this look like? So here'd be my picture. And so the magnetic field, the trend for the magnetic field lines leaving a permanent magnet, right? So it'll be, the trend will sort of be flowing from the north to the south when you're outside of the magnet, okay? So now, and again, we know that, just to be clear, that the magnetic field lines are continuous. They don't ever stop because there is no magnetic charge. I'll just sort of connect these here. But okay, so if you're looking at this here, in the before case, so let's just say I've got two magnetic field lines. So the way I've drawn this picture, the easiest way for me to look at it is I'd say, okay, so I'd have two magnetic field lines pointing out like that, okay? So first of all, everyone okay with that idea? And so now if I raise this magnet, okay, closer to the wire, so at some time after, will there be more lines pointing out or less lines pointing out? What do you think? There'll be more. Okay, so now that you've got that picture, discuss this with your neighbors again and see if you change your mind or keep your mind the same with your choice from before. So my picture would be before, like 2, and then after there'd be like maybe more, some amount more pointing out like that. Okay, and so I'm getting agreement with what I would get here. So again, and I think, so it's definitely still controversial, but I think we're agreeing here. And so again, the idea with this one is the induced magnetic field I would want to make is I would want to make it going into the page to cancel out one of those lines coming out. And so into the page would have an induced current of clockwise. All right, so Monday we don't have class.